The ideal gas law is a simple, convenient way to calculate or predict an unknown thermodynamic property based on known quantities. However, there are three big assumptions underlying the equation. The first is that gas particles are point masses, that they don't take up any space. Second, the particles are in constant random motion, in all directions equally. Third, that the gas particles experience no intermolecular forces. They don't attract or repel each other. These give rise to two corollary statements. The first is if the gas particles are point masses and in continuous random motion, then their temperature must be proportional to their kinetic energy. Second, if the particles are in constant random motion and experience no attraction or repulsion, then all collisions are perfectly elastic and instantaneous. Whether we realize it or not, real gases do take up space. We can't compress them indefinitely into zero volume. They also attract or repel each other. Think of water vapor attracting other water vapor molecules to coalesce into clouds. Also, their motion isn't necessarily entirely random. Sometimes they'll all move together, like wind. So this means that the ideal gas model doesn't necessarily apply to all situations. It can be a pretty rough approximation. But here's the thing. All models are approximations. It's really up to us as the scientist or engineer to decide whether a particular situation requires a complicated, computationally demanding, intense model, or whether a simple one, like the ideal gas model, will give a solution with sufficient accuracy and precision to meet the need of the situation. Let's work through a couple examples. In our first example, a weather balloon is filled with 100.0 liters of helium at 0.98 atmospheres and is launched from the ground, where the air temperature is 20 degrees Celsius. The first question is what mass of helium was needed to fill it? Second, calculate its volume when it reaches 10 kilometers in altitude if the balloon pressure and temperature are 0.18 atmospheres and negative 52 degrees Celsius, respectively. And so we find that to carry out this experiment, we'll need a balloon with material that can stretch to at least 410 liters, more than 4 times its original size. Anything less will burst before it reaches its target altitude of 10 kilometers. We can justify the use of the ideal gas law in this case because helium is a small, monatomic gas with negligible interatomic interactions. At the pressures, volumes, and temperatures in the question, the assumptions we made to build PV equals nRT apply, and we can trust that the result is more or less reliable. So let's start our second example. Emergency oxygen generators on some aircraft use a reaction between solid sodium chlorate and iron. The resulting oxygen gas is blended with cabin air to provide 10 to 15 minutes of breathable air. How many grams of sodium chlorate are needed to generate 125 liters of oxygen at 1.00 atmospheres and 20.0 degrees Celsius. Assuming that oxygen behaves like an ideal gas in these conditions, we can use the thermodynamic quantities to determine the moles of oxygen, then use the balanced chemical equation to determine the moles of sodium chlorate. Finally, we convert the moles to the mass needed by using its molar mass. Is it safe to assume that oxygen will behave like an ideal gas in this situation? The pressures and temperatures are moderate, but oxygen is far more subject to intermolecular forces than helium. It has a directional flow, in this case, instead of random motion, and it can hold energy as it vibrates or rotates, unlike a single point mass or the monatomic helium. Plus, since we're generating it from a chemical reaction, we would want to know how close the actual yield is to the theoretical yield, especially for an emergency system like oxygen supply on an aircraft. Here's an example where we'd want to do practical experiments to validate the theory. Furthermore, we'd want to co-create the experiments with the aircraft operators, pilots, maintenance personnel, fabricators, suppliers, exports and transport safety, law and policy, just to name a few. It's in cases like this where we see how chemical science and engineering can become central to a whole network of related issues. Now, we can joke that chemistry has all the solutions, which we do, but even in this small example, we can see how our knowledge and practice complement the knowledge and practices of non-scientific fields, and that it takes many perspectives to define, analyze, and solve today's complex problems.